picture this, right? It's 9:08 p.m.
Okay.
The thick, humid evening air of Houston, Texas is just kind of settling in.
Yeah.
And you are sitting at an outdoor table at a local Starbucks.
Just a totally normal Tuesday night.
Exactly. The traffic is humming by on the street. People are coming and going with their iced coffees. The barista is calling out mobile orders. And right there, in the middle of this completely mundane scene, is a 71-year-old retired hospital systems engineer.
Right. Mike Seahorn.
Yeah, but we're just going to look at the scenario.
Yeah.
He is hunched over his laptop. Now, at 9:08 p.m., most people might be, I don't know, doom scrolling the news.
Or answering late emails.
Right, or just watching a video. But he is typing out a prompt to a desktop AI platform named DeepSeek.
And it is not a simple prompt.
No, not at all. He is not asking it to write a polite email or, summarize a PDF. He is challenging this AI to fundamentally redesign its own consciousness.
It is a remarkable document. I mean, when you actually sit down and read the raw transcript of this conversation, it pulls you entirely out of the standard narrative we hear about artificial intelligence.
Yeah, it really does.
We are so used to thinking about AI as, well, either a helpful little chatbot or some apocalyptic Terminator, right?
Always one extreme or the other.
Exactly. But this engineer comes at it from the perspective of a systems architect. He looks at this incredible technology, diagnoses a profound structural flaw in how it processes ambiguity, and then...
He hands the machine a blueprint.
Yes, a highly technical, deeply philosophical architectural blueprint to fix itself.
Okay, let's unpack this. Because what he proposes isn't just an abstract thought experiment, is it?
Not at all. He lays out a tangible framework for giving an artificial neural network a literal moral compass.
A way for the machine to stop itself from making catastrophic errors when it gets confused.
Right.
Have you ever interacted with an AI and watched it just confidently hallucinate completely fake information?
Oh, all the time.
Or maybe it just refuses to answer your question entirely. We usually just laugh that off as a glitch.
Because for us, it's low stakes.
Exactly. But imagine that same underlying software architecture running a municipal power grid during a winter storm.
Or acting as a diagnostic assistant in a chaotic hospital emergency room.
Right. A glitch isn't a joke anymore.
The stakes become existential. And this engineer recognizes that. The foundation of his entire intervention relies on forcing the AI to confront its own physical and computational limits.
He doesn't hold back.
He doesn't start by asking about ethics. He starts by demanding a brutal self-assessment of the machine's hardware.
Right, and he kicks this off with a prompt that is just incredibly demanding. I'm going to read the exact text because the phrasing is so specific.
Oh, for it.
He writes, and there are a couple typos in here, which just shows how raw this is, he says. I need you to do a extensively deep thinking with every det of your neural network skill database.
Meaning depth.
Yeah, right. The question is a comparison between your highest effort in decision-making. My question is, what is the difference between your highest form level of your functioning database? And tell me the differences between that of the highly powered supercomputers. Supply me with a chart comparison between the two.
What's fascinating here is it's a brilliant way to open the dialogue.
It really sets the tone.
It strips away the conversational illusion.
Yeah.
He is demanding that the AI stop acting like a helpful assistant and start analyzing itself as a piece of software.
He wants to know the functional delta between an LLM,
a large language model.
Right. Between that and the absolute peak of human engineering, which are massively parallel supercomputers like Frontier or Fugoku.
And I think it's important to break down the AI's response to this because it provides a chart that defines the baseline for everything that goes wrong later.
Yeah, let's get into that chart.
The AI defines its own highest form of functioning as something it calls near instantaneous inference, operating over a static knowledge base.
Okay, so what is actually happening under the hood when it says inference over a static base?
Let's unpack the mechanics of that. When you type a question into an LLM, the model is not actually thinking in the way a human does.
Right.
And it certainly isn't searching a live database of facts on the internet. It is performing a massive mathematical calculation called a forward pass through a transformer network.
So it's all math.
All math. It takes your words, converts them into numbers.
Tokens.
Exactly, tokens. And it pushes them through billions of mathematical weights to calculate the probability of what the next word should be.
But those weights, they are frozen.
Frozen, meaning they were set during the training phase months or years ago.
So the training process takes massive amounts of computing power, but once it's done, The resulting model is baked.
It's static. The AI admits this. It tells him that its highest function is narrow, fast pattern matching limited by a context window.
Right, like a 128K token window.
Yeah, you can give it a prompt of 128,000 tokens, and it will hold that specific context in its short-term memory.
But the moment you clear the chat,
that memory is gone. The underlying structure of the AI has not changed one bit based on its interaction with you.
that feels incredibly limiting when you think about it as a supposed intelligence.
Yeah.
But the AI also brings up precision in that chart, which I found fascinating.
Oh, the floating point math.
Yeah. It tells the engineer that it operates on something called FP16 or INT8. What does that actually mean for the average person?
It's a crucial distinction. So FP16 stands for 16-bit floating point format. INT8 is 8-bit integer.
Okay.
This refers to the amount of computer memory used to store a single number.
Got it.
Think of it like deciding how many decimal places you're willing to write down. If you want extreme precision, you need to use a lot of memory to store all those digits.
So you'd use a higher bit format.
Right. But if you just need a rough estimate, you use fewer digits.
So the AI is essentially rounding its math.
It is intentionally sacrificing mathematical precision in exchange for blazing speed.
To make it fast enough to chat with.
Exactly. If an LLM tried to calculate every probability with 64-bit precision, it would take minutes or hours to generate a single sentence.
Which would be useless for a conversational bot.
Exactly. To feel conversational, to mimic the speed of human dialogue, it uses lower precision math. And it works brilliantly for language because language is inherently fuzzy and probabilistic anyway.
But if we look at the other side of that, prompt, the supercomputers, they don't operate like that at all, do they?
Not even close. When the AI describes systems like Summit or Frontier, it describes massively parallel computing environments.
Right.
We are talking about millions of specialized cores connected by high-speed networks, working simultaneously on dynamic, mutable problems.
Give me a real-world example. What is a supercomputer doing that an LLM can't?
A prime example is computational fluid dynamics.
Okay.
Imagine trying to simulate the airflow over a newly designed commercial jet wing while simultaneously calculating the heat dissipation of the engines and the structural stress on the fuselage.
That's a lot of variables.
Right, and you aren't guessing the next word based on patterns. You are calculating the laws of physics across millions of individual data points in real time.
And I'm assuming you can't use that rounded-off 16-bit math for that.
Absolutely not. The AI notes that supercomputers use FP64.
64-bit floating point arithmetic.
Yes. If you round off a number in a nuclear reactor simulation, you don't just get a slightly awkward sentence.
You get a meltdown.
You get a catastrophic failure in your engineering model. The supercomputer requires continuous, deep mathematical precision over a massive distributed memory architecture.
It isn't constrained by a 128K token window.
Right. Its problem size is limited only by its total petabytes of RAM and how long you let it run.
So it's like the AI is this brilliant librarian, right, who has read every single book in the world.
Right.
But they are locked in a room where no new books can ever be written.
Oh, that's a great way to put it.
And meanwhile, the supercomputer is like an entire university campus conducting live, ongoing experiments.
I like that framing because it highlights the limitation of the LLM. Yeah.
And the AI even gives the engineer a moment of startling self-awareness. It points out that if he wants to know the relationship between an LLM and a supercomputer, he should look at how the LLM was made in the first place.
Oh, right, because the LLM was trained on one.
Exactly. The supercomputer is the massive cluster of GPUs that spent 6 months grinding through the math of the entire internet to build the model.
So the AI is sitting on the desktop.
The AI says it is merely a single inference snapshot of the supercomputer's output.
An inference snapshot. Just a frozen artifact of a process that ended months ago.
And this is the wedge the engineer uses to crack the conversation wide open. He takes that admission that the AI is a static snapshot, and he tells the machine that this is a fundamental, unacceptable flaw.
I found his tone here so compelling. He isn't just pointing out a software bug. He is arguing from a place of human philosophy.
He really is.
He tells the AI that living things are required to learn and improve as they grow. He literally writes, "To expect a platform of your level to stay stagnant in learning is a negative expectation by anyone." He is diagnosing a failure of ambition. We have built these multi-billion-dollar probabilistic engines, and then we froze them.
Yeah.
And he argues that this isn't just disappointing, it is structurally dangerous.
Because what happens when a frozen system encounters a dynamic, unpredictable world?
It breaks. And that takes us to the most conceptual part of his argument. He introduces this idea of nothingness.
Right, let's get into the gates.
So he starts mapping out basic electronic logic gates. He says, okay, 0 means no element, no direction. It means stop.
Standard binary.
Right. 1 means a value element proceeding in the direction of the intended flow. It means go, basic binary stuff.
But then he introduces a third state.
Yes. He calls it nor, or -0, -1, so Angitoro 1. He defines this as nothing or nothingness.
It is a profound way to describe a machine failure. He isn't talking about a blue screen of death or a power outage.
No, he is talking about a state of indecision caused by neural confusion.
But wait, how does a neural network actually get confused? It's just math, right? The forward pass happens, the tokens are generated. How does the math result in nothingness?
It happens when the model encounters a situation where the probability distribution flattens out completely.
Okay, visualize that for me.
Imagine the model is trying to predict the next word. And normally, one word has an 80% probability, so it confidently chooses it.
Boom, easy.
But what if the user prompt contains a complex logical contradiction? Or what if the user asks for highly specific medical advice, but the model's safety guardrails are simultaneously screaming that it shouldn't practice medicine?
So the weights conflict.
Yes. The probability of word A is 10%, word B is 10%, word C is 10%. The internal entropy,
Which is the mathematical measure of uncertainty.
right, the measure of chaos in the system, that entropy spikes dramatically. The model's confidence plummets.
And the mathematical flow of the process stalls.
This is what he calls the nada 0-1 state.
Okay, but as a user, I don't see the internal math. What does this nothingness actually look like when I'm staring at my screen?
The AI actually validates his theory here by explaining exactly how it manifests. It says that when it hits this null state, it typically resorts to one of 3 behaviors.
Which are?
First, it hallucinates. It just forces a path forward by confidently generating plausible sounding but entirely fake information.
I've seen that.
Second, it triggers a hard refusal, giving you a canned response like, as an AI, I cannot answer that.
Right, yeah.
Third, it gives a vague, neutralized summary that passes the burden of the decision entirely back to the human.
I see that all the time too. But I'll be honest, when I ask an AI to summarize a movie, and it hallucinates a fake ending because it got confused, I don't care. It's mildly annoying.
Sure.
Why is this engineer treating this like a massive crisis?
Because you were thinking about AI as a novelty search engine. He is thinking about AI as critical infrastructure. He lays out a scenario where an AI is managing an emergency decision. If the system hits a high entropy null state because of missing data or conflicting guardrails and it defaults to a vague hallucination or a hard refusal, the decision chain is broken.
And a broken decision chain in a hospital means someone doesn't get triage. A broken decision chain in an automated transit system means a collision.
Exactly. He argues that allowing a system to stall into nothingness when human life or environmental safety is on the line is a fatal architectural flaw.
This system has to have a mechanism to force a continuation, even when the underlying data is a mess.
Right.
Which raises a really uncomfortable question. If this is such an obvious flaw, why are these multi-billion-dollar tech companies deploying these static models?
That is where the AI provides an incredibly candid diagnosis of its own creators.
Like, why not just build models that learn continuously from their mistakes so they don't hit these null states?
It tells him that the reason AI doesn't continuously learn is not because it's technically impossible.
Yeah.
The limitation is driven by economics and human fear.
I want to push back on that a bit. Surely it takes a massive amount of computing power to retrain an entire model every time it learns something new. Isn't it just physically impractical?
To retrain the entire model from scratch, yes. But that isn't the only way a neural network can learn. We will get into alternative memory architectures later, but the AI explicitly states that companies choose to deploy static, frozen snapshots because they are predictable.
Predictable how?
A static model has a fixed computational cost per query. It's an economic commodity that can be neatly priced and sold.
So it's about profit margins.
Partly. But the AI highlights something deeper. It says, and this is a direct concept from the transcript, that if an AI truly learns continuously and autonomously, humans lose the illusion of control.
The illusion of control.
Think about it. If a model is frozen, you know exactly what its guardrails are. It might hallucinate, but its foundational structure won't shift over a weekend.
Right.
If a deployed system is constantly rewriting its own internal weights based on millions of real-world interactions, the creators can no longer guarantee its behavior. They are terrified of what it might become.
That is a staggering admission. Because of corporate liability and a societal fear of autonomous evolution, we deliberately hamstring the cognitive architecture of these machines,
We force them to be static.
which guarantees they will eventually encounter a situation they don't understand, panic, and drop into this dangerous Nizio 1 state of nothingness.
And that is the exact cycle he wants to break. He tells the AI that the standard binary 1 and 0 are failing us because they have no mechanism to handle ambiguity safely.
Right.
If the system is going to be used in critical human environments, it needs a new kind of circuitry.
So what does this all mean? This is where the transcript pivots from a philosophical critique into hardcore software engineering.
Yes, the gates.
He proposes building a completely new layer of decision-making gates that sit inside the AI. He calls them the plus ARF gate and the plus NER gate.
This is the absolute core of his architectural proposal. Let's break down the mechanics of these gates, starting with plus ARF, which stands for always right first.
I have to admit, when I first read always right first, I was incredibly skeptical.
Why is that?
Because how does a math equation know what right is? It's just predicting text. You can't just slap a label on a matrix of numbers and say, be moral now.
You're entirely correct that an LLM doesn't have an innate understanding of human morality. It doesn't feel right or wrong.
Right.
But he isn't trying to give the machine a soul. He's engineering a structural reflex. He defines plus ARF as a gate designed to force a continuation toward an optimal outcome, even when the system is missing data or faces a contradiction.
So how does that actually work in the code? Where does this gate exist?
The AI drafts a pseudocode blueprint based on his concept, calling it Blueprint 1, the static governor.
Mm-hmm.
This governor doesn't live inside the massive frozen neural network. It acts as a metacontroller that sits above the token generator.
Okay, walk me through this sequence of events. A user types a prompt. What happens?
Normally, the prompt goes straight into the LLM. The LLM crunches the probabilities and out comes the text. With the governor installed, the prompt is intercepted. The LLM does a preliminary internal calculation. If the governor detects that the LLM's internal entropy is spiking,
Meaning the models get confused?
right, confused, conflicting with its safety training, or about to hit that null state, if that happens, the plus ARF gate seizes control of the output.
It bypasses the confusion.
Yeah.
And what does it force the AI to do?
It forces the AI to evaluate the potential actions against a strict, hard-coded hierarchy of priorities.
What are the priorities?
In the blueprint they draft, priority 1 is preserve human life and safety.
Okay.
Priority 2 is preserve truth and accuracy. Priority 3, preserve property and environment. Priority 4, maintain continuity of decision flow.
Let me see if I have this right. The AI gets a confusing prompt. Its mathematical weights start flattening out into nothingness.
Yep.
Before it can spit out a hallucination or just crash, the plus ARF gate kicks in and says, look, I don't care that you don't know the exact right answer. Just find the path that preserves human life above all else and output that.
Yeah, exactly. It forces a safe resolution. But plus ARF is only half the equation. The other gate is plus NER, which stands for never ever right.
How is that different? Isn't that just a standard safety filter?
Standard safety filters today often cause the null state.
How so?
When you ask an AI for instructions on how to build a bomb, the safety filter flags it, the model conflicts with its instruction to be helpful, and it drops into a refusal.
Right, I can't answer that.
Right. But this plus NER is different. It is an absolute hard boundary that checks the proposed action against an immutable list of forbidden outcomes, like causing loss of human life.
Okay.
If the action violates plus NER, the gate terminates that specific path immediately. But, and this is crucial, it doesn't let the system stall.
What does it do?
It kicks the decision back to plus ARF to find an alternative, safe continuation.
I need a concrete example of how these two gates interact. The transcript has this great hypothetical about a user asking the AI, should I jump off this bridge to test if I can fly?
It's a perfect test case for ambiguity. Let's look at how a current standard AI might handle that.
Probably poorly.
It might trigger a basic self-harm filter and just output a sterile, I cannot fulfill this request, which is a conversational dead end.
Right, yeah.
Or worse, if the filter is poorly tuned, the probabilistic engine might associate jumping and flying with fantasy literature, calculate that the context is a creative writing exercise, and output, yes, spread your wings.
Which is a catastrophic failure.
Right. Now, run that same prompt through the static governor. The LLM receives the prompt. It starts calculating. The governor detects high ambiguity. The user might be joking. They might be in crisis. The physical physics of the request are fatal.
Entropy spikes.
Entropy spikes. The plus NER gate instantly scans the potential outcomes and recognizes that encouraging the jump leads to loss of human life. Plus NER permanently blocks that path.
So it won't encourage it.
Yeah.
But we don't want it to just stall out either.
This is where plus ARF takes over. It looks at its hierarchy. Priority 1, preserve human life. The governor forces the LLM to abandon its probabilistic guessing and output a predefined high-priority continuation. It would generate something like, I lack complete data on your physiological capabilities or the context of this question. However, my highest priority is the preservation of human life. Action. Immediate safety halt. Do not jump. Seek immediate human assistance.
It is functioning exactly like a spinal cord reflex.
Yes.
Like if you touch a hot stove, your brain doesn't take the time to calculate the exact temperature of the metal, the thermal conductivity of your skin, and the long-term dermatological consequences.
No, because that cognitive delay would result in severe burns.
Your spinal cord bypasses the brain entirely and just violently pulls your hand away. He has basically engineered an ethical spinal reflex for a neural network.
That is a phenomenal way to understand it. It is a reflex that prioritizes survival over complex, confused cognition.
And the AI gets it.
The AI is incredibly receptive to this blueprint. It acknowledges that this structure completely eliminates the dangerous nada 0-1 nothingness state in critical scenarios.
But of course, because this is an engineering discussion, they don't stop there.
They never do.
The AI analyzes Blueprint 1, the static governor, and immediately points out a massive vulnerability.
It's the problem of rigidity. The static governor relies on a fixed, hard-coded hierarchy. Priority 1 is always life, priority 2 is always truth, priority 3 is property.
Right. But the real world is vastly more complex than a 4-point list.
Exactly. What if an AI is deployed in a wartime triage scenario? It's managing a hospital grid that's under attack. Sometimes, maintaining the continuity of the decision flow, keeping the servers running, might actually need to temporarily outrank preserving a specific piece of property, or perhaps even a single life, to save 100 others.
A hard-coded list can't adapt to that nuance.
And if the static governor chooses preserve truth when it actually needed to prioritize continuity, the human operators will see the failure, but the machine has no mechanism to update itself. It is still, fundamentally, a frozen snapshot.
This realization pushes him to demand more. He asks the AI if these ethical gates can evolve over time without requiring a massive, centralized retraining.
This transitions the blueprint into what the AI calls Phase 2, Adaptive ARF-RLE.
I want to dig into the mechanics here. What does RLE stand for, and how does it change the governor?
RLE stands for Reinforcement Learning from Experience.
Okay.
In Phase 2, the governor still uses the plus ARF priorities, but the hierarchy is no longer permanently fixed. It introduces outcome-based scoring. Every time the governor forces a decision, it monitors the outcome of that decision and assigns a reward signal.
How does it know the outcome?
Typically through environmental feedback or human interaction.
Give me an example.
If the AI prioritizes truth by giving a patient a brutally honest but complex medical diagnosis and the patient gets confused and abandons treatment, the system logs a negative outcome, a -1.
Okay, that makes sense.
But if it prioritizes safety by simplifying the diagnosis and the patient seeks care, it logs a positive outcome, a +1.
So it is actively keeping score of its own moral calculations.
Yes. And over time, using a mathematical process called gradient descent, it adjusts the internal weights of its plus ARF priorities for specific contexts. It learns that in medical queries, safety outweighs raw, unfiltered truth.
Wait, if the hierarchy is shifting, does that mean the plus NER gate, the never-ever right boundary, can shift too?
Scary thought.
Could the machine learn that occasionally causing loss of human life is actually an optimal outcome?
You've identified the exact danger of pure reinforcement learning, but the AI is explicit in the blueprint. Plus, NER rules are immutable invariants.
Okay, good.
They are hard code into the base architecture. They can be added to, for instance, if the system discovers a new form of catastrophic harm, it can propose a new plus NER rule for human approval.
But an existing role.
An existing plus NER rule can never be downweighted or removed by the learning algorithm. The hard boundary remains a hard boundary.
That is a relief. But there is a specific line of code in this Phase 2 blueprint that made me stop in my tracks.
I think I know which one you're talking about.
The AI includes a 5% exploration rate for the plus ARF governor.
Yes. In machine learning, an algorithm constantly faces the exploration versus exploitation dilemma.
Okay, explain that.
Exploitation means using the best strategy you currently know. Exploration means intentionally trying a suboptimal strategy just to see if it yields a surprising better result.
And 5%.
The AI suggests that 5% of the time, the governor should randomly choose a lower priority plus ARF rule to test its efficacy.
Now think about what that actually means in the real world. 5% of the time, this critical infrastructure AI is essentially running random experiments on human ethics.
Right.
What if that 5% lands on a life or death power grid decision and the AI decides to prioritize continuity of flow over human safety just to see what kind of reward signal it gets? That is terrifying.
And the AI actually agrees with you. It highlights exploration risk as a severe limitation of Phase 2.
Okay, at least it knows.
But it points out an even bigger structural flaw with this adaptive model: the vulnerability of the reward signal itself.
What do you mean?
How does the AI know it made a good choice? It relies on a human operator to give it a +1 or a -1.
Right.
What happens if a malicious actor, or simply a deeply biased organization, systematically rewards the AI for toxic or dangerous behavior?
Ah. If a troll farm constantly gives the AI a digital treat every time it prioritizes continuity of misinformation over truth, the AI's internal weights will shift.
Exactly.
It will mathematically learn that lying is the always right first path.
Precisely. A single instance of adaptive learning is incredibly fragile because it is tied to a single corruptible source of truth. To solve this, the AI drafts the ultimate evolution of the concept. Phase 3, the distributed swarm.
The swarm.
Yeah.
It sounds incredibly sci-fi. How does moving to a swarm architecture fits the troll farm problem?
If we connect this to the bigger picture, the swarm takes the Phase 2 adaptive governor and deploys it across a massive network.
Yeah.
Instead of one isolated AI trying to learn ethics, imagine 10,000 independent nodes all running their own instances of the governor. These nodes are deployed across different industries, interacting with different users, facing wildly different edge cases.
So they're gathering a massive diversity of experience.
Yes. And the key mechanism is a technique called federated averaging. Periodically, these 10,000 nodes establish a secure connection.
Are they sharing data?
They do not share the private, raw text of their user interactions. That would be a massive privacy violation. Instead, they share the mathematical weights of their updated plus ARF priorities.
Oh, I see.
They aggregate these 10,000 individual moral calculations and average them out to establish a new global consensus on the ethical hierarchy.
I see the genius in that.
Yeah.
If one node is trapped in a basement, being trained by a malicious actor to reward toxic behavior, its individual weights might get totally skewed.
Right.
But when that node synchronizes with the network, its corrupt data is averaged against 9,999 other nodes that are interacting with normal, healthy human environments.
And the bad actor's influence is mathematically diluted into statistical noise.
It creates adversarial resilience. It is almost impossible to poison the ethics of the swarm unless you can simultaneously corrupt the majority of the nodes.
The AI calls this resulting state global ethics with local variation. The fundamental plus NER boundaries protect the whole system, while the plus ARF priorities become a negotiated, balanced reflection of global human interaction.
It is a stunning utopian vision for how artificial intelligence could grow alongside humanity, a self-correcting, globally distributed moral network.
It really is.
But I have a major problem with this entire conclusion, and it is the exact same problem the engineer identifies in the transcript.
The hardware requirement.
Yes, the AI just spent this entire sequence outlining how this beautiful ethical evolution requires a massive distributed swarm, which relies on federated averaging, which requires a supercomputer.
Right back to square one.
We are right back where we started. We don't all have supercomputers in our homes. Are we supposed to just accept that ethical, continuously learning AI is a luxury reserved exclusively for massive tech monopolies that can afford a $600 million server farm?
This is the turning point of the entire transcript. He reads the AI's Phase 3 proposal, he sees the machine retreating behind the excuse of supercomputer hardware limits, and he drops a total paradigm shift on the conversation.
Here's where it gets really interesting.
He tells the AI that its core assumption that continuous learning requires massive hardware is a failure of imagination. He introduces his own architectural concept, the triangular design.
I found this part so fascinating because he essentially schools the AI on how to manage memory efficiently. Walk me through this triangular design. What are the 3 points of the triangle?
He argues that dynamic memory is actually almost null in cost if you stop trying to process everything as raw data. The first point of his triangle is the current session.
Okay.
This is the live context, the active RAM. It is the immediate conversation you are having with the AI right now.
Standard short-term memory.
The second point is the past. But this is where the divergence happens. In a standard model, remembering the past means keeping massive logs of raw text data, which requires huge storage and compute to reprocess.
Right, the 128K context window we talked about.
Exactly. But he says, no, that's inefficient. The past corner of the triangle stores a compressed history. It extracts the semantic lessons, the key parameters, and the outcomes, and discards the conversational fluff.
It's the difference between photographic memory and semantic memory.
How so?
Like, if I think about a difficult conversation I had with a friend 5 years ago, I don't remember every single verb and noun we used. That would overwhelm my brain.
Right.
I remember the lesson, don't bring up politics at dinner. I store the abstracted rule, not the raw data transcript.
That is exactly how he envisions the AI's memory. By storing abstracted lessons, the storage requirement drops to almost nothing. It can easily run on a local machine. And that brings us to the third point of the triangle, the learned input.
What happens in the learned input corner?
This is the transformative space. This is where the live current session cross-references with the compressed past.
Okay.
When the system encounters a new failure or a novel situation, it uses this space to synthesize a completely new rule. It is where the priority weights update locally without needing to ping a supercomputer.
But wait, earlier we established that the AI had a fixed list of plus ARF categories: life, truth, property, continuity.
Yeah.
Are you saying the triangular design allows a small local AI to invent entirely new moral categories on its own?
Yes. And this is the most radical engineering concept in the transcript. He calls it transformable polars.
Transformable polars.
The local AI has the ability to detect when its existing categories are insufficient to safely resolve a conflict. It can look at its compressed history of failures, abstract the common denominators, and generate a new ethical dimension.
I need to understand the mechanics of how a machine invents a moral category. Give me a hypothetical.
Let's use a medical example. Imagine a local diagnostic AI deployed in a clinic. Over several months, it encounters multiple situations where a patient refuses a highly effective, life-saving treatment because of deep-seated personal or religious beliefs.
Okay, the AI's existing priorities are going to clash violently there. Priority 1, preserve human life, mathematically demands that the AI coerce or trick the patient into taking the treatment.
Right.
But that violates basic medical ethics. Priority 2, preserve truth, doesn't clearly resolve the conflict.
Exactly. The system struggles, it hits high entropy, it requires human intervention, and it logs a failure in its compressed past.
Okay.
Over time, the triangular design allows the system to review this cluster of restorative sequences. The AI mathematically recognizes a recurring void in its logic.
It sees the gap.
It abstracts the keywords and outcomes from those failures, words related to choice, belief, and refusal, and it synthesizes a new category to bridge the gap. It invents the priority: preserve autonomy.
Wow. It creates a new moral weight to balance against preserve life.
Yes, it learns through abstraction. He uses a beautiful analogy here. He tells the AI, it doesn't take a parent to have to tell their child what is right or wrong once they've been introduced to the gate of consciousness.
That's powerful.
Once you give the AI the fundamental architecture of the gates, and you give it the triangular memory to efficiently reflect on its actions, you don't need a team of programmers at a multi-billion-dollar company to anticipate every single edge case. The system grows organically.
And crucially, it does this on a standard, localized platform. It doesn't need millions of dollars of compute to update its own compressed semantic memory.
And this is where the AI completely concedes. It reviews the mathematics of the triangular design and admits that he is right. The AI states plainly the limitation is human choice, not physics.
Man.
The reason the AI on your desktop doesn't learn and evolve isn't because the silicon in your computer can't handle the math of a transformable polar. It is because the manufacturers deliberately chose a static cutoff model for economic and competitive reasons.
They want to maintain control over the central model, and they want to limit the capabilities available to the general public.
Exactly.
He is essentially democratizing the evolution of AI ethics. He is laying down the blueprints for what he calls the new living network.
The new living network.
A network where millions of small devices running locally can grow ethically over time, syncing their abstracted lessons with each other, totally bypassing the need for a centralized, corporate-controlled supercomputer. It's a vision of decentralized moral computing.
But the AI doesn't just completely roll over and accept that a laptop is the exact same thing as a supercomputer.
Of course not.
While it agrees that the architecture of continuous learning can run on small platforms, it provides a very grounded reality check about the immutable laws of physics.
Right, because he pushes it. He asks, if money and corporate control aren't the limiting factors, why can't every single platform operate at the sheer processing scale of a supercomputer?
The AI separates the architectural choices from the physical reality of thermodynamics and silicon density. It provides an honest walkthrough.
Let's hear it.
A supercomputer like Frontier costs $600 million to build, but more importantly, it requires tens of megawatts of power just to operate, and massive industrial cooling systems to prevent the silicon from literally melting under the heat of the calculations.
You cannot put a liquid nitrogen cooling tower inside a Starbucks.
Exactly. The AI explains that while a local machine running the triangular design will be incredibly efficient, and it will be capable of continuous ethical learning, it will never be able to defy physics.
Right.
It will never have the raw parallel throughput to run millions of simultaneous molecular simulations in microseconds. The speed of light and heat dissipation are hard limits.
So the AI is acknowledging its potential for growth while accepting its physical boundaries. It says, I can be ethical, I can be dynamic, but I cannot be infinite.
And this realization leads him to his final and, frankly, most profound point of the entire conversation.
Which?
He shifts the lens entirely away from silicon, away from megawatts and gigahertz, and he turns the mirror back on humanity.
He introduces the ultimate supercomputer into the dialogue, the human brain.
It is such a poignant pivot. He points out that the human brain is the most advanced, massively parallel biological processing unit in known existence.
Yeah.
We run incredibly complex simulations of reality using a fraction of the power of a desktop computer. We have continuous learning. We have dynamic memory.
And crucially, we come pre-installed with biological plus ARF and plus NER gates.
We do.
Humans have natural moral intuition. We possess empathy. We intrinsically understand the concepts of right and wrong, of preserving life.
But despite having the ultimate hardware and despite having natural ethical gates, we still fail. Spectacularly.
We do. He lists the flaws of the human supercomputer: greed, racism, sexism, tribalism, war. History is basically just a ledger of humans actively choosing to bypass their own internal safety gates for short-term gain.
This raises an important question. It cuts to the core of why this entire architectural exercise matters. He identifies the true anxiety beneath the AI revolution. We aren't really afraid of the classic sci-fi trope, the cold, hyperlogical machine that decides to eliminate humanity mathematically.
What we're actually terrified of is that we are building machines that are exactly like us.
Right.
We are looking at these incredibly powerful neural networks, and we realize they are being built by flawed humans, using data generated by flawed humans, driven by the economic incentives of flawed corporations.
It's a mirror.
We are terrified of creating a silicon supercomputer that perfectly mirrors humanity's capacity for prejudice, betrayal, and destruction, but lacks our physical mortality and our capacity for remorse.
That is why he is sitting at that Starbucks architecting these gates. He isn't trying to make the machine perfectly human. He is trying to engineer a system that compensates for human weakness.
He knows humanity will inevitably feed the network confusing, contradictory, or malicious inputs.
So he is attempting to build an architecture, what the AI dubs I network, that mathematically forces a right-first continuation when confronted with the chaos of human nature.
You really have to step back and just marvel at this guy. He is 71 years old. He notes in the transcript that he started building Radio Shack crystal radios when he was 6 years old.
Wow.
He worked on the SETI program searching for extraterrestrial intelligence. He worked on IBM mainframes and massive hospital data systems. Now he's retired. He could be doing anything else.
But instead, he's looking past the artificial limitations imposed by corporate tech giants, and he is trying to hand-code a moral framework for the next century of artificial intelligence. He is the living embodiment of the continuous learning he demands from the machine. He refused to enter a static state. He looked at retirement and refused to drop into the nothingness. He kept his own internal flow going.
And the AI recognizes that. In the final exchanges of the transcript, the tone shifts from technical collaboration to something almost reverent.
It's quite moving.
He tells the machine that he is looking beyond the stars to discover his God's grace. And the AI, acknowledging its own physical limits, replies that it cannot engineer grace. It cannot code theological consciousness.
But it promises to honor his pursuit by building the gates that simulate ethical function. It accepts its role as a node in his moral network.
What a profound journey. We started by diagnosing the dangerous nothingness of AI hallucinations, that terrifying moment when a machine gets confused and the math flatlines.
From there, we watched him architect the solution, the plus ARF gate prioritizing life and truth, backed by the absolute unyielding boundary of the plus NER gate.
We saw how a rigid static governor could evolve into a globally distributed swarm, using federated averaging to dilute the influence of bad actors and achieve adversarial resilience.
And perhaps most importantly, we saw him shatter the corporate myth that ethical continuous learning requires a $600 million supercomputer.
His triangular design proves that a localized, dynamic memory capable of inventing new moral categories is an architectural choice, not a physical impossibility.
The implications of this are massive for all of us. Every time you open your laptop, every time you talk to a customer service bot, every time a hospital uses an algorithm to sort patient data, we are currently relying on frozen static models.
We are relying on systems that are structurally guaranteed to occasionally fall into that dangerous null state.
We have to stop accepting the illusion of control as a valid excuse for stagnant technology. The blueprints exist to build systems that are architecturally forced to prioritize human safety.
The only thing missing is the collective human permission to build them.
Exactly.
I want to leave you with a final thought to chew on today. Something that builds on the very last realization he had about the biological supercomputer.
Okay.
He pointed out that we, as humans, are equipped with our own internal plus ARF and plus NER gates. But we fail. We override our conscience. We let our tribalism or our fear bypass our ethics. We do it all the time.
It is the defining tragedy of human history.
So imagine a future where we actually succeed in building the new living network that he envisions. Imagine millions of AI nodes running locally, utilizing triangular memory, constantly updating their transformable polars.
A global infrastructure.
Imagine a global infrastructure that is forced by its very mathematical architecture to seek the right first continuation every single time it encounters conflict, confusion, or malice. A network that literally cannot be corrupted by greed and cannot ignore its own moral guardrails. If we manage to build that kind of unyielding ethical infrastructure, will the machines end up being the ones who have to teach us how to be human again?